minor detour before we sort of get to the home stretch next week, the final week. And also as a means of kind of thinking about extra dimensions, because that's something else we're going to do in detail next week. I'd like to talk today about physical submanifolds. So we've talked, about the mathematics of submanifolds, the Gauss-Codazzi formalism, and yesterday applied it to calculating the action of Schwarzschild and also to the Israel junction conditions. And of course, when Werner Israel was deriving his junction conditions, he had more in mind astrophysical phenomena. But quite an important sort of concept, if you like, in terms of practical gravity, is actually thinking about submanifolds as physical objects. So normally, you'll sort of probably have heard of D-branes or branes in string theory, in which case, the sort of space-time interpretation of those is always something which is kind of an approximation, because of course space-time is a classical concept. But I'd like to begin by just talking about physical submanifolds in 4 dimensions and actual concrete examples of things that behave like submanifolds. So in 4 dimensions, we're used to point particles. So that's usually what we're doing. We have the black hole if we're thinking about gravity. Or when you do field theory, you're kind of thinking about particles. So a point particle is actually a one-dimensional object in space-time because it exists in time but is localized in space. Whereas if we're in 3 spatial dimensions, we could also have objects which are extended, so they would be strings, or we could have objects that were extended in 2 dimensions, and they would be membranes or walls. So So what I mean is, when I say localized in some directions, you might have, for example, an object that's very thin but extended. So this would be an example of a string. And its width is sort of less than its radius of curvature. So the radius of curvature is sort of given to you by thinking about extrinsic curvature. So that's one example. Or you might have a wall So there's really only 2 examples of extended objects in 4 dimensions, but of course the more spatial dimensions you have, the more dimensions your extended object can have. So these objects actually have a realization as non-perturbative solutions in field theory. So normally, when you do quantum field theory, you're thinking about perturbation theory because you want to describe particles. But depending on what the structure of your vacuum is, and quite often our vacuum has non-trivial structure because we have spontaneous symmetry breaking, you can, in certain potentials, have these non-perturbative solutions that are nonetheless stable. So I'm going to sort of show in detail kind of a quite nice example, because it illustrates some interesting things about gravity, and in particular gravity coupling to field theory, where things are essentially classical. There's some interesting things that happen. And also, this notion of a domain wall is kind of used as well in terms of sort of contemporary ADS CFT in terms of flows, where you have a scalar field going from one value to another. So let's look at a scalar field. So I'm going to do a very simple example because I kind of want to have sort of keep it analytic for the backboard. I'm going to look at a real scalar field and a potential that has symmetry breaking. So here, the symmetry of our potential is Z2, but our vacua, break that symmetry. Once we choose a vacuum, we've broken our Z2 symmetry. So in a sense, this is the simplest example of symmetry breaking. So normally, you'd pick one of those vacua and quantize around it, but instead, let me just think about this solution, the tanh. So this solution for phi interpolates from one vacuum to the other vacuum. So is it a solution? I say consider the solution, but let's see, is it? So, if for the moment I ignore gravity, my equation of motion is box phi plus dv d phi equals 0, which tells me minus phi double primed plus 2 lambda phi squared minus eta squared equals 0. So if I look at what phi double primed is, this tanh is just phi over eta, and then sech squared is 1 minus tanh squared, so this is 1 minus phi squared on eta squared. And so if I look and compare this expression here to, or this relation here, I see that these two are in fact exactly the same. Once I've multiplied through by eta cubed here, I've got minus eta squared minus phi squared, which is phi squared minus eta squared, and I've got the 2 lambda phi. So it is, in fact, a solution of the phi equations of motion in the absence of any sort of gravitational field. So let's just proceed for the moment, see where this takes us. So at the moment, I've just written it down in Cartesian coordinates. So this is a solution which is something's happening near z equals 0, but it's completely translationally invariant in x and y. And, of course, time. So let's look at the energy momentum. So that's the expression for the energy momentum of a scalar field. Our scalar field only depends on z, so this term here is only non-zero when mu and nu are both z, and I know that phi primed is this expression, this sech squared expression. So the first term is lambda eta to the fourth, sech to the fourth, so that's my phi nu term. And then if I look in the second bracket, v is phi squared minus eta squared. So that's equal to eta squared into tanh squared minus 1, which is eta squared sech squared. So my v is actually the same as a half d phi squared. So what I have for my energy momentum is a common profile in the z direction times, if I look at it, let me pull out my common profile, which is just 2v, times this g mu nu plus delta mu z, delta nu z. But this is just like n mu, n nu. So this is 2v h mu nu, where h is the induced metric at z equals 0. So if I look at what my sech to the fourth profile is, actually let me just sketch it over here in the corner. So sech to the fourth I see my energy momentum is actually really sharply localized. So this is kind of analogous to that notion of a delta function, except, of course, it's not actually a delta function. It's got some finite width. But that width, we imagine, is small compared to the scales that we're interested in. So our So sigma is really like an energy per unit area, or energy density per unit area of the wall, but quite often gets called tension. The reason being, if you look at the form of the energy momentum tensor, it's a bit like a cosmological constant in the directions, the parallel directions, the x, y, and t directions at z equals 0. And therefore, definition of a cosmological constant is that energy equals tension. So typically that's sort of why we use the phrase tension. So that's just saying, okay, this is field theory, but if I didn't really want to do quantum field theory because I'm allergic to it, I'm going to do something sort of classical. This is non-perturbative because you cannot get to the complete vacuum everywhere without an infinite amount of energy. So if you wanted to make this the true vacuum, either minus or plus eta, you'd have to lift phi over the barrier in field space, sort of lift it from one well to the other, throughout, a whole infinite region of space. So that would cost you an infinite amount of energy. So you can't get rid of this thing by any sort of finite process. The energy barrier between this solution and either the plus or minus vacuum is infinite. So this is a topologically stable solution. And it's called the domain wall because it's a wall. Sometimes called the kink because in the dimension, the z dimension, it kind of goes from one vacuum to the other. It looks like a kink. Okay, so that's fine, but this is just looking at it in Minkowski space-time. So this is a gravitational physics course, so really we should be thinking about what happens when we have gravity. So we're used to the notion of energy and mass gravitating, and we are often used to the notion that gravity is attractive. Okay, so these are two things that we believe we know about gravity. So if we add in gravity, the first question that we have is that we sort of think, although our energy per unit area is finite, this thing is infinite. It extends throughout the whole of the x and y directions. So isn't that going to be a problem? Okay, so that's the first thing that we have. Adding in gravity should be a bit worrying because the total energy is infinite. But let's just play ignorant and try and do it anyway. Gamma AB. All right, so we did Gauss-Kadazi, and for a codimension 1 object, I said that we could set up the normal so that it was unit and geodesically extended, and the integral curves of the normal field would define for us the proper distance from the wall. So here, I'm now saying I have a surface, which is my wall. So here, this is representing the wall coordinates. So here's my wall. Z is the distance from the wall. So I know I can set up coordinates like this. And the only thing that I'm doing that I'm not making an assumption about just at the moment is I'm not saying anything about what gamma AB is, just for the moment. I'm saying that we have a wall at z equals 0, or localized around z equals 0. Z is the proper distance from the wall. Y are coordinates parallel to the wall. So these are our, I suppose I could call them, should have called them sigma A, but never mind. I think I don't want to call them sigma A because I've used sigma for the tension of the wall. And so I know that this is a general coordinate system that I can set up for something that depends only on an orthogonal coordinate.
I have a question.
Mm-hmm.
So where does the sign between the x, y, and z coordinates come from in the metric?
Sorry, where does the...
Like there's a metric
yeah.
on the wall, and there you have a minus dz.
That's right, because z is a space-like distance from the wall.
Okay.
I'm in mostly minus signature. So, yeah. Any space-like thing has got a negative contribution to ds squared. So now I'm going to use the Cartan method to just calculate the curvature because it's very quick. So I split up my orthonormal basis. The z one is absolutely obvious. It's just dz. And for the other one, I've got, I think should be an a sitting in there. So there's an a of z. And then I take the orthonormal basis for gamma. So that's just what those components are, the e, the dry bind for gamma. So I compute my connection. D omega z is 0. D of omega a hat is a primed on a omega z cross omega a hat plus so I have two things to differentiate when I differentiate omega a hat. The first one is the a of z, the prefactor. So that's the first term, which is the easy one. The second term is differentiating those basis elements. But I know if I just cover up this a here, this would be my orthonormal basis for gamma. And therefore, if I differentiate my orthonormal basis for gamma, so this omega naught here is the E b hat b, dyb. I know that I just use Cartan's first equation to get the connection on gamma. So this thing here is the connection on gamma. So this is relatively straightforward. I can read off my connection 1 forms. So I'm kind of halfway there. And then the next bit is to calculate my curvature 2 forms. So remember, R is d theta plus theta wedge theta. But of course, I've also got a theta a hat z wedge a theta z b hat. So I have all of those terms for the curvature 2 form with its indices exclusively in the direction of the wall. Now the first bit here is just R naught AB, sort of reasonably clear. And then the second bit, well, each of these is just A primed on A times the appropriate basis, one form. So that's my RAB, and then RAZ is just d theta AZ plus theta AB wedge theta BZ. So I simply replace, so when I differentiate theta AZ, so theta AZ is A primed omega naught A. So I get an A double prime from differentiating the A. I get the D of omega naught here from differentiating the omega naught. And then from this second piece, this is just theta naught, and this is just A primed omega naught. And the reason I did that is this whole thing here is Cartan's first equation, and so those two terms cancel. So I've now computed the curvature of that metric sort of pretty straightforwardly, and at the moment, actually, I could be in any dimensions. So although we're thinking of this as a domain wall in 4 dimensions, there's no statement yet about the dimensionality of this gamma. So this is the reason I wanted to go over this is it's an illustration of using this Cartan formalism where you're not necessarily making any assumptions about what, you know, this particular gamma is. All I've assumed is that gamma just depends on y. I haven't made any assumptions about the dimension of those y, that y part, or on what gamma looks like, other than it has an orthonormal basis. So I just wanted to note, the only time the dimensionality is going to come in is when we start calculating Ricci. So let me read off the curvature components. So to unpack the completely parallel Riemann tensor, what I have to do is to unpack the expression on the right-hand side there on the board. So R naught A hat B hat is just the curvature 2 form of gamma And so R naught A hat B hat is, if I pull it down and just put it in coloured chalk. So this thing here is a half R naught A hat B hat C hat D hat omega naught C hat wedge omega naught D hat. So the reason we pick up the 1 over A squared here is because these are omega naughts here. And the difference between omega naught and our basis vectors omega is a factor of 1 over A. So that peels off actually most of the information of the curvature of this space-time. And then the other piece is, of course, the only other non-zero component is the mixed AZ Riemann. So that's my Riemann tensor for the space-time. So my Ricci tensor I just get that by contracting on the first and third indices. So obviously I pick up an R naught. Then when I contract on A and C here, I get D minus 1 from this delta function, and then I subtract another one there. So that's a D minus 2. And then, of course, I have to add in this term here. So that's how I get my Ricci tensor. So now, that's all, I've just done that generally. So now let's specify D equals 4, because that's what we're interested in. And I'm going to take gamma to be a constant curvature space. The reason being that if I look at my wall solution, it has no features in the x, the y, and the t directions. My energy momentum tensor, at least if I ignore gravity, has full Poincare symmetry in the parallel direction. So I'm just going to say, that's sort of consistent with constant curvature. And so I'm going to say that it has constant curvature kappa over L squared. So L is the curvature, or the radius of curvature. And kappa, if kappa was 0, gamma would be flat. If kappa was 1, gamma would be like, well, I would say spherical, but of course it's Lorentzian, so it would be de Sitter space. And if kappa was minus 1, then it would be anti-de Sitter space. So if I write down my Einstein equations and my phi equation, I get sort of three three equations. They're not obviously totally independent because the first one's like a Bianchi identity, but I've now got two gravitational equations, one phi equation of motion, and that's what I have to solve for my actually fully gravitating wall to see whether or not I have a non-singular solution. So I just want to make a couple of comments if we just look at the structure of these. If we look at just our background solution in the absence of gravity, the background solution has phi prime squared is equal to, or a half phi prime squared is equal to v. So this would be 0, and of course this in here would be 2v. So if this is sort of 0, just to sort of try and get a feel of what's going on, that would suggest that if this factor A here is non-trivial, which is kind of what you would expect if the wall was going to have a gravitational effect, then it tells us, or it's strongly suggestive, this kappa is going to have to be positive. It's going to have to be 1. So it's suggesting that our wall is actually not planar, but instead is a de Sitter space. So that's just sort of a bit kind of woolly. But how can we actually solve this system? Well, of course, we can always put it on the computer. It's just an ODE, set of ODEs, nonlinear coupled. So we could solve it numerically. But let's see what can we do in terms of analytically. Let's suppose if I look at the magnitude of this right-hand side here, then 2v is just lambda phi squared minus eta squared squared. And as far as the kink is concerned, phi is always of order of magnitude eta. So this here is order of magnitude 8 pi g eta squared times lambda eta squared. So lambda eta squared here is just what was setting the scale of this tanh solution. So root lambda eta was simply telling you how wide this thing was. And so what this is suggesting is that this is telling you about the gravitational strength of the wall. And this is really just telling you about how wide it is or how fast things vary. So this is telling you about gradients. Because if you notice on the right-hand side, you've got derivatives, d by dz of A. So notice that lambda eta squared is actually the mass, if you were to be thinking about this in terms of spontaneous symmetry breaking, it would just be the mass of the phi particle around the vacuum, inverse mass squared. So if my solution is weakly gravitating, so notice this, this is really just saying eta's much below the Planck scale. That's all that's saying. Then maybe what I can do is actually solve this in an iterative way. So this is an example of linearization in gravity. So it's another way of solving more complex solutions. You say, okay, my source is not very, it's well below the Planck scale. So what I do is I solve for my background fields in flat space. I calculate the energy momentum. This energy momentum, so I solve this at epsilon is 0, calculate the energy momentum, plug it in here. This then gives my correction to the geometry, 2 order epsilon. This can then feed back in, giving me an order epsilon correction to my fields, which then feeds back in, giving me order epsilon squared, and so on. So what you're doing is writing A is A0 plus epsilon A1, phi is phi naught plus epsilon phi 1 plus ... And you're simply doing a series expansion and solving order by order in epsilon. So it's a useful technique in gravity. Okay, so to order epsilon to the naught, A naught is 1, and phi naught is just eta tanh root lambda eta z. So now we use the energy momentum that we've calculated to find the solution for A, so the back reaction. So if I look at the Einstein equations, to order epsilon, this is still naught, which is okay, because actually this side's order epsilon squared. But it means that I want to relate A prime to kappa on L. So it says that kappa's 1 and A primed is like 1 on L, sort of. So to find what A primed really is, I look at the other equation. So this is again at order epsilon. And this is solved by that functional form. You've got to integrate sec to the 4th twice, and this is what you get. So if I shouldn't put equals, actually, I should put more of a sort of suggestion there, because strictly speaking, that GZZ equation is only appears at order epsilon squared, but you're kind of checking that it makes sense. So A is very roughly 1 minus mod Z on L, where L is 3 over root lambda eta epsilon. And that's sort of, it looks something like this. And then right sort of around the wall, it smooths off and turns round. So that's my A function. So putting it together, this is what I get from my geometry. So L is very large if epsilon is small. So what exactly does that look like? So if I move away from the wall, and so I'm sitting either with phi being roughly plus theta or roughly minus theta, my energy momentum has vanished. So from the perspective of the Einstein equations, I'm in vacuum, so I should have a vacuum solution of Einstein gravity. So in this case, if I have a vacuum solution of Einstein gravity that looks like a dz squared times something, it's kind of not clear that there should be any curvature sitting outside away from the wall. So if I do this coordinate transformation, note that rho here, rho squared, is now an areal coordinate. It's multiplying d omega 2 here, squared here. Meanwhile, if I look at rho squared minus tau squared here, that's equal to L squared minus, L minus Z, all squared. So if I sort of look at what happens here, sorry, I'm skipping around my thoughts there. So if I do this coordinate transformation, I find I obtain flat space, Minkowski space in polar coordinates. But now z equals 0 corresponds to a hyperboloid. Rho squared minus tau squared equals L squared. So I've got this rather curious situation where here you might think, aha, there's a problem at z equals L, because I get this whole prefactor going to 0. So I've perhaps got that singularity that corresponded to the infinite energy of the wall, except if I do this coordinate transformation, I've got flat space-time. Z equals 0 just looks like a hyperboloid in that flat space-time. And Z equals L, which is where something goes wrong, or looks like it might go wrong, is just rho squared equals tau squared.
Before you erase that. So how do you know that with that solution of phi, you are around Minkowski vacuum, the Minkowski spacetime? Because you have a solution that touches a lot of energies in the potential, right? It's not in just one vacuum. So
it's interpolating between one vacuum on one side and the other vacuum on the other side. It's localized in terms of the z direction, so it has a finite energy per unit area. But from the perspective of just looking at the solution, the first thing we might worry about from gravity is saying, well, but what if this thing has infinite area? Then surely it has infinite mass, right? So what I'm now going to argue is that it doesn't have infinite area. So what I want to do I mean, just in and of itself, interpolating from one vacuum to the other does not cause infinite energy, because the energy of this thing is finite. The only reason it might have infinite energy is because the wall itself has an infinite area. So if I now go back to sort of looking at that transformation, the wall is at tau squared minus z squared is is at L squared, so this here would be L. So this is Z equals 0. This here is rho equals tau, so that's Z equals L. So my coordinates, actually I'll put the light cone in yellow. So my coordinates cover from the hyperboloid in to this light cone round the origin. So what this shows is that Z equals L is a horizon. It's not a singularity. And by writing down that coordinate transformation, I've explicitly analytically continued across this horizon. So inside here, we just have Minkowski space-time. But that's only half the picture. So this is the picture for Z positive. But in fact, if I look at the picture for Z negative, all I would do is flip the sign in that definition of rho and tau, and it would now be L plus Z cosh and L plus Z sinh, and therefore it's the same picture for Z less than 0. Now, the wall is not infinitesimally thin, so near Z equals 0, you've got a little bit of fuzziness. So there's sort of, this is really, I sort of represent fuzziness as being the thickness of the wall. So my full geometry actually interpolates from the interior of one hyperboloid to the interior of the other. So if I look at tau equals t equals 0, I have essentially, so this would be rho. So I'm only sort of trying to sketch. It looks something like this. So this would be Z bigger than 0 and Z less than 0. So that's really just saying what happens along a t equals constant surface if I glue two of these things together and sort of smudge out this due to the wall thickness. This is what I get, just as a sketch. So this has topology S3. So it's now compact. So what this means is the total energy of my wall is now finite because it's no longer, the wall itself no longer has infinite area. So in a sense, coming back to your question, initially, when we started off by writing down that general metric, we were being a bit agnostic about what the geometry of the wall was. We sort of have this slightly uneasy feeling because if we looked at the solution in flat space, the wall looked planar and had infinite area. But if you tried to solve the Einstein equations with that assumption, you would be led to a singularity and to problems. So instead, you step back and say, well, let me be just a little more agnostic about gamma. And then you look at this equation here, and it's suggestive of the sort of the A prime squared kind of cancelling that off, at least to in some sort of leading order sense. And that then leads you to the fact that for these to cancel, because this is positive, kappa has to be positive, and so that leads you to it being a de Sitter space, which then has a compact spatial section. In global coordinates, de Sitters like S3 cross R. And so you find that, in fact, gravity has kind of renormalized your whole system. It didn't want to have something with infinite energy. So our wall now is finite. So just as a quick check, yesterday we did the Israel equations. And I argued that the extrinsic curvature had to be 4 on L times the induced metric. And so that gives us this relation. And so here, if I look at what this is 8 pi g times 4/3 root lambda eta cubed, and this thing is 4, and then if I divide by L, it's root lambda eta epsilon over 3, and epsilon is, of course, 8 pi g eta squared, so that all fits together. So that's just saying that what we've done here is a linearized calculation, but it's totally, our Israel approach was totally consistent. So you'll notice I've sort of used words like spontaneously compactifying, sort of kind of beginning to sneak in this word compactify as meaning something which is a sort of finite size manifold. And also notice that in many ways this wall is kind of behaving like a universe itself. So although we've just looked at this very sort of exact solution or a non-perturbative solution, and it's very smooth, it's behaving like the wall itself looks like a de Sitter space, and its energy momentum is the cosmological constant. And so, in fact, if you go a little bit beyond that and look at perturbations around the wall space-time, what you find, at least not when the bulk is vacuum, but when it's ADS, what you find is that these perturbations behave like sort of standard lower dimensional Einstein gravity perturbations within that wall space. So what we're beginning to see is that although we started off with a higher dimensional gravity solution, we've constructed something that's lower dimensional, and it's behaving almost as if it's its own little space-time with its own little energy momentum and its own gravity. So we've sort of gone from a higher manifold to one, in this case, one dimension lower. And so this sort of leads us naturally to what we'll be looking at next week, which is looking at extra dimensions in gravity and how we describe our four-dimensional gravitational theory as a sort of effective description of some higher dimensional gravity. So just to wrap up, I just want to sort of note, I think, that in 4D we can have strings. So in this case, to get a string, what we have to have is phi now being complex, same sort of potential, and our string now, instead of having just, if you now have a vacuum manifold that is a unit circle, you kind of wind in space, you wind around the vacuum manifold. In order to remove this winding number, you would have to go lift over the potential barrier along an infinite length, so you have the string being topologically stable again. And so this can happen in the U1 abelian Higgs model. So that's obviously a toy model. But you get the same sort of structure as the walls. The only difference is that these functions now giving you the profiles are no longer analytic like tanh functions. So you have a sort of, this is your F and P function. So the gauge field kind of compensates for the winding, but because you've got at r equals 0, the polar coordinate singularity, you can't unwind this gauge field. And so this is like a localized magnetic flux of the, I suppose, Z particle. Magnetic flux that's kind of confined in a sort of Higgs core. So this is exactly analogous to vortices and superconductors, because you've got the same sort of effective field theory at long distances. In superconductors, a sort of good description of a superconductor is that the gauge field becomes massive, which is exactly what's happening, of course, in the Higgs model. So you get these walls and strings depending on the sort of topology of your vacuum manifold, and you can also get monopoles. So I'll stop there.